Let's take a look at example 2 to see how we can actually make use of the power rule in a couple different specific situations. First, a quick recap of the power rule. Remember that the power rule stated that as long as n, which represents the exponent, is any real number, it has to stand for a number, then if I wanted the derivative of the variable of x raised to that number as a power, then this would be a way to actually state the derivative without going through the big scary limit. That is, we could identify that the pattern that we were seeing back in example 1 was correct, and therefore we can use that instead of computing the limit every time. Now, if we take a look at example 2, we're going to notice right off the bat here in example 1 that we're being asked again to calculate the derivative of this function. Remember, that's what this notation means. This d over the dx says take the derivative of the following. You can kind of almost imagine that similar to like when I have a square root symbol. This says take the square root of, and then I have to put something inside of it to finish the symbol. Right? So like take the square root of 4. This says take the derivative, and then I have to fill something in the parentheses to state what I'm doing the derivative of. But this says take the derivative of 1 divided by x. And immediately I notice I have a problem. 1 divided by x is not, or does not currently look like, x raised to a power. And the power rule can only help me take the derivative of a variable raised to a power. So I'm going to go ahead here, and I'm actually going to just do a little bit of rewriting of the inside of this notation. I still need to take the derivative here, but I'm going to note that 1 over x could be rewritten as x to the power of negative 1. This is a very useful skill to recall in Calculus 1. So if this is true, now I do have x to a power. It's just that that value of n is negative 1. But according to the power rule then, to take its derivative, I would put the negative 1 in the front, and I would lower the power by 1. So I would subtract 1 again from this negative 1. So that means that this would decrease to negative 2. So this here would represent the derivative. Of course, this could be potentially re-expressed as negative 1 divided by x squared. So there we go. There's my use of the power rule. Now, if you take a look at part B, you'll see that in here, I'm asked to take the derivative, this time with the variable of t involved. And I already have something that's t to a power that is a number. So I can get right to calculating this very quickly. This is going to be bring the 1.7 to the front, and then remember I'm going to have to subtract 1 from the original power. So that would just bring it to 0.7. And it's totally fine to have like awkward decimal values up there. Not a problem. Take a look at part C though. Here again I'm back to something where I don't quite have my variable of s being raised to a power. It is raised to a power, but then it's also inside of a fifth root. And so the power rule doesn't help me with that. There's nothing in here about what to do if there's a root on the outside. So again, I'm going to pull a little bit of an algebra move first, and I'm going to rewrite the inside before I take the derivative. Remember that any time that I have a root, like a fifth root or a fourth root, or really any root at all, I can rewrite that as an exponent with 1 over the value of the root. So if this is a fifth root, I can do a 1/5 power. Now, I can see here I have s to the 7th all to the 1/5. And that still doesn't quite fit this form yet. So I'm going to do another algebra step and kind of combine these powers. Remember, if I have a power to a power, I multiply those two powers together, and so I can get s to the 7/5. Now this looks like this. I have my variable raised to a numerical power. So I can bring that power to the front, and then I can try to lower my power by 1. Subtracting 1 from that would be the same as taking away 5/5, because 5/5 would be 1, so that would leave me with a power of 2/5. So this is how I would make use of the power rule. Now, an important question to maybe ask at this point is, could we use the power rule to figure out this derivative? Here I want the derivative of the function x to the power x. What do you think? Could I use this power rule here? Well, my answer to this should be No. And the reason why is that it actually doesn't fit the form of the power rule. Notice that my power rule has to have x raised to any real number. And I don't have x raised to the n. I don't have a number up there. I have a variable. So here I'll state that the power is a variable and not a real number. So I do have to be careful here to make sure that I only try to use the power rule when I specifically have the setup that the power rule requires, which is that x to the power of a number.